Thank you.
Thank you.
Bye bye.
I had a bush. I went and washed my face and came.
माथै दुख्ने गरेर लेख्यो
Sleeping pig too.
Oh.
Saranga is sleeping in class.
Were you actually asleep?
And,
Yeah, I was like, then I went out.
and Jacob is focusing on the subject.
I wouldn't say focusing. I was pretty confused. I was
Yeah.
like, what the?
But like the fact that.
Because I got up and came back, and I was like, well.
It's like magic.
If you have an in-person exam, we'll be open book.
Yeah.
We will bring all the material and just flip the page, flip the page.
You know,
flip
like
the page. So,
this and quantum being like that means like it relieves so many things.
We still need to study.
Yeah, we have to study, but imagine.
I know.
It's like,
We can't be complacent, even if it's open. So like.
yeah, we need to know how to apply, but we don't need to bypass theorems and stuff.
I know. That's good.
For example, in mathematical exam last time, I forgot that E.
So, just because it's open, so like my electrodynamics course in undergrad, open book, open note, open homework, whatever. Even though all that sounded great, it didn't matter.
Oh.
It's either you knew it or you didn't. But, yeah. I don't care. I'm gonna study just as hard as if it was.
Oh, you two more.
This card for my country, Saudi Arabia.
Oh.
Because my dad called the call.
How many hours behind?
Huh?
How many hours? What's the time difference?
I think 9 hours.
9 hours.
Yeah.
9 hours?
Because one different time. No.
Yeah. We have the
Now-
biggest difference.
Now
10 and a
1
half,
o'clock.
right?
1 to 23 a.m. No.
Oh.
Oh, there.
Yeah.
In Saudi Arabia.
Yeah. It's,
In Nepal, it's maybe
4
4:15, about 2
PM.
a.m.
A.M. I think, hi, how are you? 4 hours between Saudi and
Yeah, maybe.
yeah.
In the same continent, so not too capital.
No, Jacob.
Would you like that apple?
Yeah, where is my shout?
Oh, well, no. You have to come here for that. Would you like an apple?
No, thank you.
Would you like an apple?
no, thank you.
Okay. Which one?
This
This
one.
one? Okay.
Thank you, Jacob.
Okay.
तपाईँलाई र मलाई राखेको हो क्या खानु
होइन
होइन खुरम न त
खानुहोस् क्या
हाँ?
खानु नि तपाईँ
तपाईँ आएपछि खाने भनेर मैले बिहानै दिएको थिएँ अर्जुन के अरे अनिललाई र मलाई होइन बिहान नआएको
खानुहोस् लेट्स ग्राब इट के बुझिनँ मैले यो क्लासिकल
मास्टरमा पढ्ने बेला मजाले बुझिएको थियो नि
यस्तो
पढेकै हो त यो
रिप्रेजेन्टेसन पढायो नि त हामीले
यो कन्सेप्ट नै पढेको हो त अनि
हो कि त
बिर्सिनु भयो
यस्तो
तर यो त अहिले
पढाएको थिएन
हँ?
यस्तो कम्प्लेक्स गरी पढाएको थिएन यार
खै कसरी पढेको थियो पढ्न चाहिँ पढेको थियो त्यही खोजेर पढ्दा हुन्छ भने भनेर It's tasty.
Yeah. Just go eat in front of the camera.
Thank you, Jacob, for this wonderful show.
You are blocking.
Oh!
Very, very juicy.
Oh, Suranga.
Do we have to do the
Ishuranga? Hello,
before-
Ishuranga.
Hey.
Do you like apple?
Would you like an apple?
Who doesn't know?
Yeah.
Do you like?
Okay, that's
There you
fine.
go.
You have?
Yeah, yeah, yeah.
Oh, we can break this into.
Oh, no.
No one is interested. You and me.
Okay. You have?
Yeah.
Okay. Thank you very much. Oh, no, for the salad.
Yeah, yeah. Thank you.
No, thank you. You have to pay some money. Thank you doesn't work.
Thank you, that's not much. How do you say thank you again? I keep on forgetting.
Dhanyavad.
Yeah.
In English,
No,
in Nepal.
Oh,
This is
Dhanyavad.
yeah.
a good idea actually, to avoid falling asleep.
Shukran.
Right?
Oh, yeah.
Shukriya.
Yeah.
Shukriya.
Yeah, I brought just for
Then
that.
Hindi.
Hindi.
I should do the same.
In
You
Saudi.
sound
Thank
like
you very much for the
Yeah, in
idea.
Saudi,
You're
shukran.
welcome.
Shukran, yeah. Shukriya. Shukriya India, huh? Shukriya.
Shukriya in Hindi.
Hindi,
Thank you. Like this is Brani's.
He can understand that.
Shukriya.
Sri Lanka also have many common words with Hindi.
No,
No?
no.
No, no, I think different. Which one?
Signalis is different.
You said roti.
Food. Yeah, we have those kind of.
This is the Sri Lankan word. Sri Lankan word.
Yeah, roti.
And this word also fits in Hindi as well as in Nepal.
Oh,
So that's you can find some common words.
By the way, for the quantum homework, very first question that she has us do, we literally did it in class at one point. Like, exactly the question.
Yeah?
Yeah, it's the delta xn, delta pn multiplication. If you look back, we literally did that in class, so you can use that.
Oh, cool. Hopefully the sun is not blocking it. I'm not recording. How are you?
Pretty good.
Yeah.
All right, what we did last time was Cauchy's theorem, right? If a function is analytic, then come to integral of f of z dz equal to 0. That's what we said. Today, and then I also mentioned that if if a function is analytic and you want to calculate the value of the function at the interior point, it can solely be determined by value of the integrand f of z over z minus z naught on the integral of that quantity, and that was called as Cauchy's integral formula. So this is what we did last time. So this is where we stopped last time. F of z is analytic in certain region. Okay. And z naught is a point within that region. Then the value of the function at an interior point. So this is true for f of t. The function is analytic. Then the value of the function at an interior point is given by the contour integral of, there's 1 over 2 pi I also, is f of z over z minus z naught. I dz. And this 1 over 2 pi I here. Alright, so this is what we proved last time. And what I want to do today is calculate the first derivative and the nth derivative function for analytic function, and then go to prove the Taylor's series, series for complex function, whether it's valid. And so we know that for real variables or real functions, if function is analytic, you can write a Taylor's expansion for a certain point, that we know, right? So similar thing, if it is valid or not, is what we're going to do for a complex function. And if it's not valid, what are we going to do? That will lead to another one, which is a Lorentz expansion. And Lorentz expansion is very important because it has, some term called residue, and which is what is going to lead to Cauchy residue theorem. So I'll prove Cauchy residue theorem in an indirect way today, but I'll give a direct proof next time. Okay, I mean it's standalone proof, but it is coming through the Lorentz expansion. So that's what we are going to do. Okay, so this is what we know so far. So the next thing I'm going to do is Taylor series, but to do that I need several things. Okay, so this is true for complex analytic functions too. Just as it's true for real functions. Okay. All right. So let us try to first get what is the first derivative of the function at z0. Since this is at an interior point, and so f of z is analytic both on the contour and inside. All right. So what's the definition of f prime z? Z0. We know how to take the derivative, right? And then so we can simply write f of z0 plus h minus f of z0 over h, limit h tending to 0. So nothing fancy I've done, just taking it. So, but we know what's the definition for an analytic function, what is the value of the function at an interior point, right? So I can write this as limit h tending to 0 of 1 over 2 pi I contour integral of value of the function on the contour divided by z minus z0 plus h times dz. So that's that term minus then I'm going to put 1 over 2 pi I, you know that you can take it out. F of z minus z0 dz. Everything, and I have an h everywhere. Okay, so let me also put an h everywhere. All right, so this I can write in compact notation as limit h tending to 0. This is z minus z0. So I have, basically I'm looking at this term, which is nothing but z minus z0 minus z minus z0 minus h. Okay. So that is nothing but h. Okay, there's an h. Effectively what I have is 1 over 2 pi I times h. Contour integral of c f of z dz. I have an h here which will cancel in this h downstairs, and I have z minus z0 z minus z0 minus h. So that's what I have, and I can cancel that, and with the limit h tending to 0, I can remove that also. So in the limit, what I have is the following. So for an analytic function, the first derivative at an interior point is simply 1 over 2 pi I contour integral of f of z over z minus z0 square dz. That that's what we have. For the first derivative of an analytic function at an integral point. Okay. So this you can, now you can calculate second derivative same way, right? Second derivative is nothing but, like that. And take the derivative. If you did that, and we calculated the nth derivative at z0, what do you think is the formula for it? Can you, the induction, can you tell me what's going to be? As a second derivative, I'm going to do that, right, whatever it is, and then I have already z minus z0 squared. You understand, I mean, so you can extrapolate that result. Just guess at least some of the things, major terms. So this is nth derivative of f of z.
Z minus Z naught over to the n.
N plus 1, right? I mean, because this is 1, this is 2, okay? But there's also a factorial developing, okay? That's why I wanted, if maybe you can do for one more and then you'll see that there's a factorial, because this is, you know, you'll see that actually. If you did one more, you'll start seeing that. So, So what we have is, do you have any questions here?
Oh, no.
So for an analytic function, it looks as though, you know, to get the nth derivative, I can, this is, if this is the definition, I can get the nth derivative by taking the derivative of as though I'm taking the nth derivative of this integrand within the integral with respect to z0. So you can see that's why you're getting this in n plus 1, and you can also understand what the impact is. Right? So this is equivalent to, this can happen only if it's an analytic function. So as though in trying to get the nth derivative of z0, what we have done is simply taken the nth derivative within the integral with respect to z0. Okay, that's what we've done. So this result is exactly the same as that. Right? The first time you do second derivative, what you will have minus z0 squared, but you're taking with respect to z0, so extra negative sign, which will make it positive. So you can sort of start seeing. Okay, so if you know this and if you remember that, you know what these are. Okay, so it's like taking the whatever derivative of the analytic function as though you're taking the derivative within the integral with respect to z0. Okay, that's how we're getting all this stuff. All right. So if knowing this, we can start developing the Taylor series and all that stuff. Function analytic complex function, something like this, where a sub n is nth derivative at variable z0 forward in factorial. This is what we write it for real function, but so if f of z is analytic, it's an analytic complex function. Can we write a Taylor series like this? Similar to real functions. Okay, so I'm going to give the proof of Taylor's theorem here. So I'm going to do slightly, I want to do f of z, which is also an interior domain point. Let me just call variables slightly differently. All right, so f of z is analytic in the domain, and z naught is, the circle C is centered around z naught, and z is any interior point within this domain R or C or whatever you want to call it. And variable C, I have trouble pronouncing this Greek symbol, that is only on the contour. Okay, so that variable is defined, it is, whatever it is, radius times exponential I theta of this. So if this is the case, now since in my definition now Z is an interior point, just notice this, this is an interior point now. Okay, and f of z is analytic, and I have, if I want to apply the Cauchy's integral formula, what should I write it as? The corresponding expression, if z was an interior point, I'm trying to, knowing the value of the function on the contour, okay, I want to say what is the value of function at z. So I want you to understand all the variables here. That's the important thing. The meaning of Cauchy's integral. What was z here when I wrote that formula? What did I say? Value of the function at interior point is determined solely by, by the function at on the contour, right? So what should I replace this by if I had to apply? I'm saying this is the variable just on the contour. I'll just flip the variable sets on the pen, it's not that. It's just 1 over 2 pi I. Contour integral of, I want you to understand all the meanings of all these things, right? And my interior point is now z, okay? Within the domain where the function is analytic. Alright, and z naught is also a point within the contour, so I can, in this domain, it's nothing that I can always add and subtract z naught, and I can do this. So z minus, this is the radius for the center, this is zeta minus 0, right? So that's the complex variable that it defines. And z naught minus z is this distance, whatever that distance is. Suppose we have z somewhere here. That is that distance. So if I choose the radius of this circle very large, I want to look at this in that limit what happens. So 1 over 2 pi I. Alright, I'm going to write this as contour integral of since this is large, I could, let me just take it out maybe. Sorry, yeah, okay, yeah, alright. Zeta minus z naught. I have 1 minus z minus z naught over zeta minus z naught. All I've done is just pull this out. Okay. This distance out, and I have got something like this. Okay. So the reason I put, I put this is like this. Supposing I have a term like this, 1 over 1 minus t. I know I can write it as 1 plus t square, blah blah blah, which is summation t from n, and going from 0 to infinity. That we can do. So because this is large, this radius is large compared to z minus z naught, I can do that geometric series kind of a expansion of the term 1 minus z naught over zeta minus z naught. Okay. So what I have is the following: f of z is nothing but contour integral of and that term, I have it, here it is there. Okay, I have this also, right? Summation n going from 0 to infinity. I'm writing in this compact notation, z minus z naught over zeta minus z naught to the power of n based on that expression. So basically I've written 1 over 1 minus z naught over zeta minus z naught as this. Okay, that's all I've done. All right, let me just write down this as so this looks like 1 over 2 pi I summation n going from 0 to infinity of what is that quantity? 1 over 2 pi I, contour integral of that is what? Derivative, and there's n factorial which you have to do, right? So which is, that's why I proved this, okay? So that at an interior point, nth derivative at an interior point is given by that expression. So what it is nothing but n factorial over, I mean it is, nth derivative of f at z naught divided by n factorial. Okay, so with it, I also have 2 pi r so that you understand. So this is nothing but nth derivative of from here, what we approved here. So what we approved is, so all we have done is we started with Cauchy's integral formula for something which is analytic, and we have obtained this expression which is nothing but Taylor's expansion, right? Summation and going from 0 to infinity of nth derivative of the function at z0 divided by n factorial, which is your coefficient a sub n. Okay, so alright, we approved that. Let me write down my coefficient a sub n. Divided by n factorial, so it is 1 over 2.I of whatever it is in this case, z was in the contour, it will be this definition. Which is also the nth derivative of the function of the hypertonic. We just keep all these definitions in mind. So what we approved is rigorously everything we approved from right from how did we start? Cauchy-Riemann. If function analytic, it should satisfy Cauchy-Riemann condition. If Cauchy-Riemann condition is valid, Cauchy's theorem is Cauchy's formula is valid. If Cauchy's formula is valid, Cauchy, how to get an analytic function at interior point, Cauchy's integral formula. From Cauchy's integral formula, we approved from first principles Taylor series for expansion for a complex function. Okay, so we did not assume anything, right? And we approved it. All we did was, okay, functionality, derivative should exist. That's all we said. And the limit, whether you go, because it's a complex function, you can reach the limit in two ways, along the real axis or imaginary axis. Both limits should be the same. That's what we said, right, last time. That's how we got the Cauchy-Riemann condition from there. So if everything is from first principles, we prove this. All right. So now this is clear. So the next thing that we want to prove is what if the function is not analytic in a given region. So let us say the function now is blowing up at z equal to z0. What kind of expansion can we suggest? Function is not analytic, that is, it does not singularity. Nature of singularity will be classified, okay, through Lorentz. Let us, for the sake of argument, assume f of z has, I'm going to define all these definitions a bit clearly a little later, has a pole of order determiner P at Z equal to Z naught. What it means is your function has a term like 1 over, your function, if something like, let's say, if you have some function, then this is called a simple pole, okay? But if your function had something like this, okay, then the function f of z has a singularity, has a pole at z equal to z naught, but it's of order p. Okay, so we have to make a distinction between the case when p equal to 1 and when it's not equal to 1, because the way we calculate residue are going to be different for the two cases. Okay, so just to understand what it is, more general case will be maybe there's something else there. Okay, so let us first derive for a more general case and then decide what to do. So yes, so f of z has something, okay, some function which is blowing up at z minus z naught, z equal to z naught, and it may blow up like 1 over z minus z naught or high power, whatever it is, right? Again, it's a singularity. So if this is the case, okay, f of z is not analytic, but I can remove the singularity just as we did previously in ordinary differential equation Parsees also, right? So if I can suggest under function g of z, which is z minus z naught power p multiplied with f of z. F of z already has singularity of the order 1 over z minus z naught p can cancel, right? So g of z, although this is not analytic, this function g of z is analytic, so I can write Taylor series for this function. Knowing that, what kind of series I can predict for f of z? That will invert the argument and find out what it is. Okay. So g of z, although this is g of z is analytic, so we can write Taylor's series expansion for g of z. So let me just, so if this argument is clear, let me just erase this, okay?
What is our P again?
P is just, okay, P is it's called, the word we use is order of the pole, okay? So what it means is the following, f of z, some function, what a complex function it could be, as I said, you have a term in the denominator which is decaying not as a 1 over minus z minus z naught, but z minus z naught to the power of p. Okay, so that p is called the order of this pole. It has a singularity at z equal to z naught, but it is how fast, that defines the order of the pole. Okay, so if it is 2, it's called second order pole. Okay, if it's 1, it's called simple pole. Okay, so there is a word for each one of them, and it is important. P equal to 1 will be called a simple pole. P equal to 2 will be second order. Simple means, first order, okay? So this one in this case is pth order pole, okay? P equal to m, or whatever you call it, mth order pole, okay? So how it decays, how the denominator looks like is, is what I meant by that, okay? And we'll come across it again and again about this, but it's important to note, it's not enough to say z equal to z naught is a pole, but how it decays, this function decays is also important, okay? All right, fine, so, okay, this is now analytic, so I can write for this something like this, right? Taylor series for the Bn is what? I'm going to distinguish equation A, N, and Bn because this is for G, and that was when A was f of z was analytic. Okay, so I want you to understand that. What is B of n? if G of Z is analytic, what is B of N? Can you call it as nth derivative? First in a simple way, right? Over n factorial. Okay, that's the simplest thing, and we know what it is in terms of integral also. Okay, so all these things will become important. Okay, let's first get this. So this is my G of Z. Now, so what is my f of Z in terms of these powers of Z minus Z naught and all that? So f of Z is nothing but, I can write it as Bn Z minus Z naught, that divided by, sorry, multiplied, is it? G of Z is that, also f of Z is G of Z divided by that, so it is n minus P, n going from 0 to infinity. Can I write that? So this looks like at this point, infinite series of this form, B0, n equal to 0, right? For first term is that. N equal to 1, so that is P minus 1. Then n equal to P, n equal to P, we have, that's 1, right? And then what do we have? N equal to P, this is n equal to P term. N equal to P plus 1 term looks like n equal to P plus 1 is 1, and so on and so forth. And what is the coefficient of the term Z minus Z naught of n? That's an infinite series, but what is the coefficient of? Can I call it B of n plus P, or P plus n? Doesn't matter which you call it. Can you call it like that? Right. So all these things are very, very important. Okay. All right. So I have given some expansion for f of z around this point z minus z naught, but I don't like it yet because why I don't like it is the following. This is b0, this is b1, p minus 1, and all that. So I cannot write it in a concise notation. Okay. So what should I do to write it in a concise notation so I can, in a summation notation, I want to write so that, I can put a summation and give a different, connection between b and another coefficient, right? I mean, I want to give it. Let me just write down and see. Let me see that. Understand that. So supposing I call this term b of n plus p as a sub n. Can you guess what these terms will be and how I can write this series? Call this term, okay, I want this as a n z to power z naught for n kind of a thing, okay? Then, and also it gives very nice meaning to everything. When do I get b0? Can I call that as correspondence between B0 and the coefficient A. Can I write this first term as A minus B? That is A0 is nothing but, A minus P is nothing but B0. This is the correspondence. Once I have that, I have all these things, right? So this one will be what? I want this Z minus Z naught about P minus 1. Okay, so this is A minus, I want this to be what? B1, right? So this is P minus, sorry, B1. Yeah, P1 minus P. Minus P plus 1 if you want, minus P plus 1 if you want. Now, so if we continue with this, what is the term? So this was AN. Oh, let me just go. This became AN Z minus Z naught of N. Okay. Now, in this series, okay, what does BP correspond to? We just said, what was it? B of N plus P is A sub N. What does this term correspond to? A0, right? You can put N equal to 0 and get that. So this is A0. Okay. And then this term is A1, Z minus Z naught, and so on and so forth. Is this clear? Why is this translation important? So f of z, I have written in the following way. So there's one more term is very important. I should write down. Alright, the most important term in this Lorentz series is this term, okay? I'm going to erase this because you understand what it is. The term before that is what? A minus 1, okay? And so what we have is this series has become, this is the Lorentz series basically. You have p terms. If the function has pth order pole, you got a minus p, the coefficient will not be 0. Okay, that's what it means by pth order pole, and it has such terms. And this part is analytic. This doesn't have any problem, right? This is an analytic part of this function. This one is called as principal part of this function, and what is it? I have written this function f of z as, instead of the Taylor series, I'm having what? Z minus z naught to of n, a sub n, except now n goes from negative p to infinity. It looks like Taylor series, except it is, so if you had, let's say, infinite such term, if I made this minus infinity to plus infinity, what does it tell you about the nature of singularity at z equal to z naught? We started with the fact that our function f of z has a, some singularity to order p. That's what we started with. And so we removed that singularity by multiplying by that. So that's what we did. Okay. Now, I know f of z does not have Taylor series, but g of z has Taylor series. From there, what kind of series expansion can I give, right? So you have some terms which have inverse power of z minus z naught because it has singularity. So that's clear. It has singularity of order p. So the leading term is that. Okay. If you have a function which has singularity of 2, what is the leading term? Supposing I have a function something, just to understand what we are trying to do. Supposing I had a function like this, what is the Lorentz series expansion for, without the details of, forget, let me just input one. What is the Lorentz series expansion? What is the leading term which is not 0? What is the leading coefficient which is not 0? If a function is analytic, you don't have any of these terms. You have only that. That is your Taylor series. If f of z was analytic, you don't have any of these terms, right? Because it's well behaved. If f of z is not analytic, it has singularity at z equals z naught, and the singularity is like this, and I want to write the Taylor's expansion without doing much. I mean, which is the leading term, which is leading coefficient which is non-zero? I'm trying to understand whether you understand the meaning of a minus p and stuff like that, p at the whole and stuff like that. That's what I'm trying to understand.
So does this mean for any non-analytic or function, the principal part will dominate at the singularity?
I'm going to talk to you about that because this series has to converge. So that's an important point, okay? I mean, this is why I'm trying to ask you, I want you to understand how many such terms are there, okay? It is the balance of the two will eventually tell you whether series exists, whether for the function f of z, I can write such a series, okay? May now. So that's why I was also trying to probe you by saying, if I had infinite terms, what does that mean? What does that mean for what is at point z naught? So Lorentz series is also used to characterize the nature of the singularity z naught. Okay, so this is Lorentz series. So if I had only this term in f of z, it still has singularity. So what is the leading term coefficient I will have? A minus 1. All the others will be 0. Okay, so that is your Lorentz expansion. A minus 1 and some analytic part perhaps you have. Okay. So if it is this, it will be a minus 2 z minus z naught squared and the rest. Okay, so a minus 2. That's some coefficient that we have to calculate, and I'm going to, those are important coefficient and they have got meaning, okay, because we know what those coefficients are. Okay, so if you have, if there are infinite such terms, of course, it's got essential singularity. Z naught is essential singularity. So maybe you have something f of z is something like this exponential of 1 over z minus z naught, right? Because I cannot. There's no way I can remove it because 1 plus x squared over, whatever, that. This is, I got n such terms, right? I mean, such a function will have, infinite, z naught will be a singularity of nth order, that is essential singularity. That means I have a minus infinity, there are many terms of. Okay, so that is the order. The meaning of p is, which you asked, is the order of the singularity. For essential HP is infinity. Okay, so that is the meaning of it.
Is it ever useful to find closed form answers of the analytic part and then the principal part? So being like, for one of our functions being like, the analytical part becomes, this function by its series, and then we have this garbage that we add to it.
Yeah, I'm going to talk about, we will do for some functions, like the Lorentz series expansion. You will see what is the analytic part and what is the thing, all that stuff, right? You will see that. How these expansions are done for a real example. But the most important thing, okay, convergence, such a series. So we know there is singularity somewhere. Okay. In this case, we have to, we may be trying to eliminate that point. So Lorentz series is actually convergent only in an annular region. Okay. So let us say this is C2, this is C1. Z0 is, depends on how much you have. I mean, so it's always how much is this part dominant and how much is that part dominant dictates, where the series is convergent or not. So for Lorentz series, it will be convergent in the annular region. That's also. Now, the most important thing here is this term, this coefficient is an important, plays a major role, a minus 1, which is the coefficient of the term z minus z naught. This is a very important term, okay? And it's called as the residue, okay? I'll tell you, this is the whole thing here, to use the Cauchy's integral formula, how to calculate a minus 1 is a major part. Today we'll try to learn how to calculate residue through Lorentz series expansion, but next time I'll give you simpler methods to calculate residue, very easy, you don't have to worry about it, but the origin of the whole thing is from here. Why is that important? Okay, let's, so what is a minus, let's see what I have done. Okay, so this is also important. So if you have infinite series, infinite order pole, essential singularity, this Lorentz series starts at minus infinity to plus infinity. Okay? It's a pth order pole, it starts at n equal to minus p, right? That's what we have shown. So where it starts tells you, the order of the pole. If it's n equal to minus 2, you have second order pole. Okay, so that's the meaning of it. But otherwise it looks like almost like Taylor series, right? Except that's it. But what is an for us? We know what is bn because that is the what we got from your what is it called? This is what we got from our Taylor's expansion. So we know what is bn, which is given by this formula. Okay, I know how to calculate nth derivative because that's also there, right? And then did we calculate nth derivative from another formula? Okay. Let's the nth derivative of is given by this formula, right? N factorial this. Is it correct? We just proved it. N plus 1, sorry. It is one higher, right? Sorry, that was for the interior point. Yeah, so this is nth derivative, okay. We have, this is the formula for nth derivative, that we know. Where is that? Okay, here. But what is the relationship between Bn and a coefficient An? What did we say? The coefficient Bn was An plus P, right? So we know the relationship between An and the coefficient B. This is how. I know how to calculate this, I know because that's analytic, I know that, right? So from here I'm going to calculate the coefficient An and in particular A minus 1. Okay, that's what is going to lead to Cauchy residue theorem. Okay, let's first write An. What is An? So let us Bn, the coefficient Bn is what then? Coefficient Bn is 1 over n, in fact I can remove that, so it's simply 1 over 2 pi I contour integral of g of z minus z naught from n plus 1 dz. Okay, is this clear? All I've done is, this came from that definition of Taylor series, and I substitute for the nth derivative. Okay, so I calculate that. Okay, now, and I need to calculate b of n plus p to get the coefficient an. All right, is this clear? All right, so. All right, an is nothing but b of n plus p, based on, in this Lorentz series, expand to the coefficient a, and we are related by that. So what it means is a sub n is nothing but 1 over 2 pi I contour integral of g of z minus z naught n plus p plus 1 dz. Okay. So I have an expression for these coefficient a's here. But what is gz? I want to write it in terms of my original function, right? I mean, the function f of z, which is cut similarity. So what I get is the following. A sub n in terms of f of z is nothing but 1 over 2 pi I. Where is that? G of z is the following. Z minus z naught of p, f of z, okay, I'm substitute for this, n plus p plus 1 dz. Alright? Or all I've done is substitute for this using the original assumption that, what's it?
Is our z in the annual region,
What did you say?
or z,
Function, yeah.
or variable?
Yeah, right now, it is there, but the function, but f of z is convergent only in this annular region. Okay, so z is within the annular region. Eventually, for the series to converge, okay, that's where it will eventually reside. Okay, I mean, although z is also defined within it. Okay, so z is there, but it is only z naught. It is blowing up. Okay. But because it's got two parts, which is a part which is going up and part which is well behaved, it is going to be, the net result of it is that that function or that series is convergent only in a part of the region, which is annular region. Okay. Okay. Now what is okay? This is what it is. I'm substitute. Okay. Went from here to here, right? G of z is that. So I can cancel p. So what I have is an expression for a sub n, which is the most important one. I have the coefficient a sub n, which is in the Lorentz series expansion, is nothing but, I can cancel p, right? What else can I do? Okay, 1 over 2 pi I contour integral of f of z dz z minus z naught to the power of n plus 1. Now, if this is the case, what is n, this coefficient a minus 1? Because I want to calculate what is called as residue, right? That's the most important thing in the whole Lorentz expansion eventually.
Calculate integral of f and z.
Right, 1 over 2 pi I contour integral of f of z dz. So this is what we call as Cauchy-Residue theorem. So what it says is the following. The Cauchy-Residue theorem, what it says is, if a function f of z is sort of blowing up a certain region, not everywhere, some points in the domain, the contour integral of f of z dz is nothing but 2 pi I times a minus 1, which is called as residue of the function f of z. So our whole task will be how to calculate this residue of the function in an easy manner for different integrands, so that, and then I'll do different kind of contours to calculate infinite integral, right? So f if f of z was analytic in the domain, what should be the right-hand side? Supposing f of z was analytic in the entire region, what is that integral? Contra-integral f of z to z. 0. That is Cauchy's theorem. But if f of z is got some singularities, okay, so this is what we'll do next time. I'll give a standalone proof, which will be easier. I mean, in the way we did it, and we'll draw a contour to eliminate it and all that, so that we know that f of z is then analytic in the other region. Okay. So we have to calculate what is the residue of the function about z equal to z naught. That's our task. But if the many, in a given problem, you may have several singularities too. It's not just one singularity. Maybe there's maybe in a different region. Supposing I had z minus 1, z minus 2, then I have singularity at z equal to 1, z equal to 2 and all that, right? So the Cauchy residue theorem, what it says is the following. Contour integral of a function f which is not analytic in a domain, okay, it's blowing up as z equal to z1, z equal to z2 and all that. You have to calculate the residue of this function at all these points, all these singularities. So you may have under summation over j, okay, j is all the singularities in the domain, okay, within the domain, enclosed by the contour. That's also an important thing. If I draw a contour something, whatever it is, eliminating that, I don't have to do it, calculate the residue. So the whole task of drawing a proper contour is to minimize my task, draw it so that some things can be eliminated, so that I have only calculate once, in the path of the integral, whatever we have to calculate also depends on that. So j here is summation over all singularities enclosed by the contour C. So those are important points. So this is your Cauchy residue theorem proved from Lorentz series. So this is a very interesting one, right? Supposing you may be having, all it says is a closed contour. It doesn't care how you draw the closed contour. I mean, many times we'll do a semicircular one, okay? And maybe you have to calculate an integral from minus infinity to plus infinity. This is where the important thing comes. It's a closed contour. Go from minus infinity to plus infinity, and then a semicircle, that is a contour. And you take the radius of this very large, so that the integrand goes away. I mean, it doesn't contribute because you have z minus z naught in the denominator that will not contribute. On this line, it will not contribute. And you'll be able to calculate the integral from minus infinity to plus. So you break this contour C into various parts, right? Minus r to plus r to whatever it is. And you'll be able to extract such integrals, provided you know the right-hand side, which is how to calculate the residue. Supposing this function is blowing up certain points, you need to calculate, what is this quantity a minus 1, which is called residue of the function, at all these points within the contour that you have chosen. Okay, so that will depend on the problem that you are being asked. It could be 0 to infinity or minus infinity. You draw a different kind of circle. Yeah.
It seems like there would be a significant change if we were to draw our contour at where a singularity is just past the edge of it.
What do you mean past the edge of it?
So we have two singularities here and here, and we draw our contour around just this one, barely just missing that one. It seems like there should be some sort of...
Yeah, I mean, those are things will happen, okay? I mean, like, it can happen even on the real axis. Like, supposing you have a function 1 over z, and I have z equal to 0, right? I mean, is a singularity. Supposing I had a function like this, okay? Something like this. I will have singularity at z equal to 0, okay? So what I'll do is I'll draw again, I'll try to bypass that point, okay? Then I have to calculate the contribution from that semicircle. But in the limit r equal to 0, most of the time there will be contribution from that. So all that, you know, we have to play with. It depends on the function, right? Whatever function you have. And so maybe you cannot use contour integral if maybe there are some cases where you cannot do it also. Because in order for me to use these kind of methods, and I supposing I want, most of the time why am I using this method? I mean, I'm not interested in contour integral, but I'm interested in calculating such integrals.
I think a better way of saying it is that previously we established that the shape and the shape of the contour didn't matter.
Yeah.
But now it can.
No, because you got a singularity, right? That was for analytic function. The shape did not matter if f of z was analytic, right? Now, it is not analytic. It is sitting on your real axis. I mean, on real axis. Yeah, that is strictly true for f of z is analytic, and that's where it didn't matter only endpoints and stuff like that. So yeah, that's an important point to understand. Okay, so this is the central theorem of the whole thing, and our task is to calculate this residue. Supposing there may be cases there is a singularity in the upper half plane and the lower half plane, right? Doesn't matter if you minus infinity plus, you can go this way or go that way. You should get the same answer. Okay, so those are some tricks we will, we'll apply all these kinds of things, and the direction of how we traverse the contour is important, clockwise, anti-clockwise, and all that. What's the time? Can I do an example for Lorentz series, or it's already? I can do it, right? Yeah. So I want to. So is this clear? I mean, all you have to remember is if it's a function of singularities, the order of the pole is driven by how many terms inverse power of z minus z naught you have. Okay, second order pole, you will have two such terms. Okay, pth order term, you have p such terms. Okay, but regardless of the order of the pole, the term which is most important is this a minus 1. Okay, which is what leads you to you have a way to calculate the infinite contour integrals. From contour integral, you can calculate infinite integral. So all the methodologies from now onwards will be focused on this. Okay. So you have to remember that you should calculate that all the residues which are enclosed within your contour. That's an important point. All right, let's today we are going to do a complicated way of calculating a minus 1 through the Lorentz series. But I'll give you a very easy method. You don't have to worry about it next time. Okay. So based on this, if you're able to expand the function somehow in terms of analytic part z minus z naught and the 1 over inverse power of z minus z naught, all you have to identify is what is the coefficient which is multiplying this term 1 over z minus z naught. If you can identify that term, that is your residue. Okay, this is what this method says. Okay, the coefficient of the term 1 over z minus z naught is your residue. Now, let's understand this. So what are the poles of this function? So it's a complex function, this is a complex variable. What are the poles of this function? How many poles does it have? 2 locations, right? It is z equal to minus 1, it is going up, z equal to minus 2, it is going up. And so I will have corresponding to z equal to minus 1, I will have one expression. Corresponding z minus 2, the other expression for Lorentz expansion, a minus 1 for both of them will be different. Okay, different kinds of expansion. Let's do for first for z equal to minus 2. In all these things, somehow you have to expand. If like you have 1 plus or alpha z or something, you 1 plus whatever now t. You need to expect. You need to know the binomial expansion of those series. then it becomes easier. That's you need to know how to convert a function into series form using binomial expansion, all the things that we have done. Okay, like that. You know that 1 over 1 minus t is nothing but 1 plus t plus t squared, blah blah blah. Right? 1 over. So it's, you know, or binomial expansion. Okay. So supposing z, so that's a simple pole. Okay, it's not squared or something. It's a pole of p or whatever you call it as 1. Okay, pole, a simple pole. In this case, and what was I going to say? Yeah, let me call this variable u. So u could 0 whatever I want to do the expansion. Okay, that is what I'm trying to do. So f of u is nothing but u minus 2. Z plus 1 is u minus 1, and z plus 2 is u. So when so u is equal to 0 and z tends to minus 2. Okay, the pole is equal to minus 2. We need to calculate residue at z equal to minus 2. That's what we're trying to do, and the Lorentz expansion corresponds to that. So I can write this as, let me put a negative sign so that I know I can write this as 1 minus u. So we know how to expand 1 over 1 minus u. So f of u is 2 minus u, and 1 over 1 minus u is that 1 plus u plus u squared, that's an infinite series like that. So this is nothing but what? What are the terms here? The pole of order 1, right? Z equal to 2 was pole of order 1. What's the leading term here in this case, in the Lorentz expansion? How many terms are there in powers of z minus z naught? What is the highest non-vanishing coefficient here? Because this is simple pole. I have only one. This is the only term. All others a minus 2 a minus. We will not have all these terms in this case, right? It's a simple code. Okay. So I'm just saying it's already coming there. So I wanted to show you. So this is nothing but the first term is 2 minus. Let me just see. That's okay. Let me call it 2 over u minus u1, right? 1 plus u plus u squared. So the first term is 2 over u, right? And the second term is minus 1 okay, here. And then I have a plus 2 coming from here, okay? Just a few terms I want to show you, right? I mean, 2 over u, minus 1, this is 2, that is 2, right? And then I have minus u, and then I have u squared plus 2u you have, and then negative u squared and all that. So this is what my f of u has become. And then f of z, I put u equal to what? Z plus 2, right? So 2 over, the Lorentz expansion is z is nothing but plus 1. Plus u, we started with that, plus u, this is u, right, I combine that, minus, maybe something like that. So what is the residue in this case? I have expanded f of z as a singularity. Z naught is what? Z naught for u is minus 2, basically, right? So this is just Lorentz expansion now, right? With z minus z naught, right? Z naught is your minus 2, negative 2. So this is your analytic part. All these things are analytic part of your. this is the only principal part because this is a so what is a minus 1 in this case? That's 2. Okay, so that's a coefficient. So this is a little bit clumsy method because you have to know these expansions. So, but this is how it came about, and then we use this to make a very simple way to do it. Extremely simple way of calculating residue. But you need to know the origin of all these things, right? I mean, so it is. We started with a function which is not, which has got singularities. We said, okay. Then it cannot have a Taylor series, it must have something else. So the series corresponding expansion is called Lorentz series. Lorentz series will have, some inverse power of z minus z naught. And how many such, inverse power of z minus depends on the depends on the nature of the function. And if you have a simple pole, then you will have only one such term, 1 over a minus 1, z minus z naught, and the coefficient a minus. This is your a minus 1. So the residue for this function is so similarly you have to calculate the residue for in your if this was some integral that you have to calculate, you need to calculate the residue for z equal to minus 1. Okay, z naught is minus 1 in that case, right? So you also have to calculate the residue for each one of the terms for which the function is going up. So you have to do similar exercise for other singularity also, simple pole. Okay, so you can do that as an exercise. All you have to do is I did the substitution because it's easier to expand such terms, right? I mean, rather than z plus 2 trying 1 over z plus 2 trying to expand. So that's why. But just this is sort of brute force way of calculating. Like the way that once when you do not know the formula for the derivative, you have to do a brute force way of calculating the derivative, taking the limit, right? So this is a brute force way of calculating residue. But I will give you a very simple formula so that you can calculate many infinite integrals very easily. Okay? It's not difficult at all. So I will talk about that next time. Calculation of residues for different methods I give you, so that you are able to do it quickly rather than doing expansions and expansions. And then we'll do lots of applications in functions. So far we're talking about single value functions. You may have multi-values functions. F of z may have square root of z or something like that, or natural log of z or something. How do you do such integrals? Okay, so we'll have other pitfalls in our function in addition to singularities like this, to be multi-valued function also. Okay, the integrand was square root of z or z minus 2, let us say. Not only then my integrand is multi-valued also, doubly valued. What kind of contour I have to draw. So basically those are the things. My emphasis will be the type of contours I will draw, so that I can exploit Cauchy residue theorem. And I will also give a standalone proof. Cauchy residue theorem, very simple proof again. You don't have to go through the Lorentz series because it's complicated, all these things. You have to read, you have so many things out there. Coefficient A and all the integral formula for that, because it came from all that stuff. But I will give you something which is very simple way of doing that, just not in 10 minutes. So we'll continue on that.